All right, let's look at how we can apply principle of maximum likelihood to the problem of logistic regression. So remember we have y, which takes values 0, 1, and we want to predict y, but instead of predicting 0, 1, we rather predict probability that y equals to 1 given x. And we do it by taking a linear transformation of x, so beta 0 plus beta transpose x, and then we take logistic function of s, so exponenta of that linear transform divided by 1 plus exponenta, and logistic function, remember, returns a number between 0 and 1, and then we interpret this number as a probability that y equals to 1 given x. Now, since we have a probability now, we can write down a probabilistic model for y, and it's simply a Bernoulli distribution. So y given x follows Bernoulli distribution, and the probability of success of this Bernoulli distribution is given by this p of x, which is our logistic function applied to the affine transformation. Now we have probabilistic model. Now we can write down the likelihood for the logistic regression. And so what we have here, we have y follows Bernoulli, parameterized by p. I'm going to skip x just for simplicity of the notations. And the density function, you remember that probability that y equals 1 equals p, and probability that y equals 0 equals 1 minus p. And we want to put this into a single formula. Single formula for the density for the Bernoulli would be so probability over y is just p to the power y, and then 1 minus p to the power 1 minus y. Now you can check this formula. If you plug in y equals to 1 here, you're going to get p to the power 1, so it's just p, and here you're going to have something to the power 0, which is just 1, so we just have p here. And when y equals to 0, we have something to the power 0, which is 1, and they have 1 minus p to the power 1, so we just have 1 minus p. So the formula works. It's basically density function or mass function for the Bernoulli distribution. So now we can write down the likelihood associated with individual observation. So if we have pair yi xi, then the likelihood associated with this pair is going to be p of xi raised to the power yi times 1 minus p xi raised to the power 1 minus yi. And again, if we want to find the total likelihood, we're just going to take a product. I goes from 1 to n, all the observation sample. And so that's the likelihood for the logistic regression. Let's take this formula and apply it. So here we have the likelihood function of beta 0 and the beta. Again, p to the power y minus p to the power 1 minus y, and we take a product to get the joint likelihood or the joint density associated with the problem. And now we're going to rearrange this formula a little bit to make notations and modifications a little bit simpler. So we're going to arrange so that all first k y's will be equal to 1, and k plus 1 through n y's are going to be equal to 0. So we're just going to rearrange the data. Because data is IID, so it doesn't really matter in what order it appears. So we can change order in any way we want. And the likelihood doesn't depend on the order either, because the likelihood is just the product, so product is interchangeable. And then we're going to take the logarithm of that. So we're going to have a log likelihood, so which is the log of this product, and now product is going to look different depending on whether y is 1 or 0. So now we have first k terms where y equals to 1, and y equals to 1 is just p of xi, right? So we have product of p of xi. And when y equals to 0, we have 1 minus pxi, so product of 1 minus pxi. So what you see here, so this formula here is just 1 minus p of xi. If you do some simplifications, then you'll get something like 1 over 1 plus exponent of this affine transform. Okay, and now logarithm transform product into the sum. So we have sum over first k terms, and it's so we can try to expand it. So we have log, you remember, exponent of p divided by 1 plus, so let's not call it p actually, let's call it something else. So we're gonna call it I'm gonna call it a. A is gonna be beta transpose x plus beta 0, so our linear transformation of x. And so we're gonna have log exponent of a here, 1 plus exponent of a, and log of the ratio is the difference of the log, so we're gonna have log exponent of a minus log 1 plus exponent of a, and log of exponent is just cancel each other, so we have here I'm going to continue here a minus log 1 plus exponent of a. Okay, so this is your and then of course you sum it up, so this is your a here, and you sum across all the a's, and then this term basically gets into here. Okay, so that's the simplified algebraic formula for the likelihood. Now a couple of observations here, that the log likelihood is concave in beta 0 and beta 1. So first we have a linear part here, and linear function is both concave and convex. So concave is what we care about because we're trying to find the maxima of it, and concave function is the function that has unique maxima. So when we have concavity, we basically guarantee that whenever we find the maxima point, this point is going to be unique. And also this point exists, so that's another important consideration. And here we have exponenta of something, and then we have log of this exponenta. So essentially it's also a linear looking function, which tells us that what we have is a concave function. And now what we need here, the linear algebra doesn't work anymore. We cannot use linear algebra to solve this problem, so we basically have to maximize this as a function of beta 0 and beta, and you basically can use your favorite solver. So you have to use optimization solver, and given that this problem is concave, those problems are very efficiently can be solved. So even large instances, when your data set is large, number of parameters is large, can be solved very efficiently, and it's more or less given now. So you don't really need to worry about those algorithms. They work. It's a technology now. They're very reliable. They give you good solutions. So in 99% of the cases, you basically should trust whatever comes out of the optimization algorithm.